Hello and welcome to the buffer zone. We are going to be doing a buffer problem. And I wanted to go through starting out with the creation of a buffer to start with and calculate the pH of it, and then see what happens when we add a strong base to it and calculate the new pH. And all of this will be using the Henderson-Hasselbalch equation that's used for buffers. So, oh gosh, and which pen should I use? I have all these fountain pens with different colors, and I think I'm going to start with purple. Okay, so let's get rolling. Oh my gosh. I decided to create a problem using weak acid HBRO, because then it would be HBRO, which I thought was kind of silly. Hydrobromic acid. No, it's not hydrobromic acid. That would be HBr, right? So we have a different kind of anion for this. Alright, so first off, let's just talk for a moment about what is a buffer. A buffer is always a weak acid plus its conjugate base. So, when we look at this example, I want to look at H. Okay. So when we've got this particular weak acid, it breaks apart slightly to give some hydrogen ions and our brew anion. Okay, here is the conjugate base. So if we had just HBRO in acid by itself, that is all that would be there. Okay, and it would break apart into these equal amounts. However, if you put in some of its conjugate base, then that gives essentially a receptacle for this conjugate base to react with any acid that happens to be added. And we have the acid on this side that can react with a base. And so we can have essentially this equilibrium can shift to either side depending on whether you're adding an acid or a base, a strong acid or a strong base. Okay, the first thing I wanted to do is write out the acid dissociation constant. We're going to write out the expression first. Okay, so equilibrium constant, products over reactants. So we've got H plus BRO minus over the whole acid itself, HBRO. Alright, so I've told you this is a weak acid, so we can expect this value to be quite small, to be less than 1 for sure, and absolutely it is. Okay, this Ka value is known to be 2.8 times 10 to the minus 9th. Okay, pretty small. We are not seeing a lot of hydrogen ions gases by itself. Okay. Now, if we are going to be considering a buffer that is containing this weak acid and its conjugate base, it means that we will be using the Henderson-Hasselbalch equation, which looks like this. Henderson-Hasselbalch equation allows you to calculate the pH of a buffer if you know the pKa of the weak acid, and then you add the base 10 log of the ratio of the conjugate base. So I'm going to put it in here, what it is in this sample problem, divided by the acid, HBr. Okay? So that does mean we need to calculate the pKa. All right, so pKa is equal to the minus log of Ka. And if this looks familiar to you, if you're thinking about pH equals minus log of concentration of H plus, you are correct. This lowercase p, this is essentially a mathematical operation. That is the minus base 10 log of whatever is following the p. In this case, it's Ka. So pKa minus log of Ka. We can calculate that because we know the value of the Ka. So this is minus log of 2.8 times 10 to the minus 9th. And what does that equal? Well, I already put this into my calculator, and it is 8.55. Okay. Now we are prepared to calculate the pH of a buffer if we know what these concentrations are. Okay. So I'm going to give you a problem. Okay. And that is a buffer contains, because this is an aqueous solution, and it's got concentration of HBrO is 0.50 molar. Okay, and its conjugate base is 0.60 molar. And what we're going to do is we are going to calculate the pH. And now we have everything we need to do that, right? We've got the equation we need, Henderson-Hasselbalch equation, that relates pKa and these two concentrations with the pH. We know what those concentrations are, and we just calculated the pKa. So we are ready. pH equals, all right, we calculated the pKa, it's 8.55. And we will add in the base 10 log. Here's our conjugate base. That was 0.6. conjugate acid is in the denominator. That we are told is 0.50 molar. Okay. Notice how we have a ratio here where there's slightly more of the base than there is of the acid. So we have a ratio here that's greater than 1, 0.6 divided by 0.5. In fact, we could look at what that value is. Oh, here's my amazing magical calculator that always gives me some weird looking gobbledygook here. Every time I pick it up, it has something different if it's been sitting there for a while. It gets abducted by aliens, and this is some language. I love it. Anyway, okay. Let's divide 0.6 divided by 0.5. That is 1.2. Okay. The base 10 log of a value that is greater than 1 is a positive value. And you might say, okay, who cares? But this is relevant because notice how we have more of the base. And so by having a positive value here, we're going to be adding a number to this pH, and the pH will be larger, meaning more basic. So that should match. More base, higher pH, more basic. And it would be true if we had more acid. We would have a larger value in the denominator. This ratio would be less than 1. Base 10 log of a value less than 1 is a negative number, and the pH would go down. It'd be more acidic. Okay, so this ratio between the acid and the conjugate base should be relevant to how it's going to affect whether or not the pH will be greater than the pK or less than the pK. Or, if these are equal, the log of 1 equals 0, and the pH will be equal to the pK. Okay, so let's go ahead, put in these values. We divided 0.6 by 0.5. We got 1.2. Take the base 10 log of that, and we get 0.07991, etc. But if we add this in to 8.55, we get 8.63. Okay, so here is the pH of the buffer. Okay, so this is our starting buffer. Okay, but now, what if we add in some strong base? And I'm going to choose a value of 0.07 moles. And we're going to say in 1 liter of buffer. Okay, so what if we do this? What is the new pH? All right, now we get to set up an ice diagram. Okay, and we need to take into account, okay, I want to use a different color here. I love that I totally missed something here. Moles of what, you ask? Okay. hydroxide of a strong base. This is very relevant to the question. Now, I could have said strong acid. That would be another kind of problem that is related to what we are about to do. Okay. But what we need to consider is what would happen if we put in hydroxide. This is a strong base, and that strong base will react with our weak acid, our HBRO. Okay, this is our weak acid in the problem, but we are now bringing in a base. Okay, so you're going to put the weak acid and the strong base reacting together. Okay, what happens when we do that? This strong base will strip off that hydrogen ion from the weak acid. Okay, that will leave behind the conjugate base, and it will create water. Okay, so notice the phases of these. This is aqueous, this is aqueous, aqueous. But this water is liquid. Okay, so this will not appear in the equilibrium constant. There is no reason to consider what is the concentration of water. It is pure liquid. So we are going to focus on the concentrations of the weak acid, the hydroxide that we just put in, and the weak base. And we are setting up what is called an ice diagram. Okay, ice, where I stands for initial. Okay, so this is where we put in the initial concentrations of each of these components. So if you recall, we had 0.5 molar concentration of the acid, of the weak acid in this buffer. We were told that someone snuck in and added 0.07 moles in this liter of buffer. Okay, so that's the concentration in moles per liter. And in terms of this conjugate base, BRO minus, this buffer started out with 0.6 molar. Okay, so this is our initial situation. Remember, water is a liquid. It's irrelevant with concentration. Okay, now change. Okay, ICE, initial, change, and then we'll be looking at the final concentration. What we do here in this row is we look at this strong base that was added. And what happens is this gets completely consumed. So you start here and you acknowledge this has all been gobbled up. It is reacted away, it is reacted with the acid to create the conjugate base in water. Okay, this will always be your assumption here, such that the hydroxide in the equilibrium row equals 0. So these will get subtracted out. From here, you then look at the other reactant. If this is reacting with this weak acid, then this weak acid will also be reduced by that same amount. Meanwhile, the other side of the equilibrium, this is what is being created by virtue of these two reacting together. So this will be plus 0.07. Okay. Then we add these columns. Here we've got 0.50 minus 0.07, which gives us 0.47. So notice how when I said add these columns, because this is negative, we are subtracting this. That's why we get less here. Okay, and we would expect that because some of this acid reacted with the strong base. Okay, but we still have plenty left. Okay, meanwhile, we have formed more of the conjugate base. We have formed 0.07 moles more. All right, so we add this column. We now have 0.67 molar. And now these are the values we put into the Henderson-Hasselbalch equation to calculate the new pH that results from after having added in the strong base. So let's calculate that. pH equals pK plus base 10 log of concentration conjugate base over concentration conjugate acid. And when we put in our values, we use that same pK value that we used above, the 8.55 we already calculated. Now we have log BrO minus 0.67. 67 molar divided by 0.43. Okay. And this gives, we've created more base, so we would expect the pH to go up. That's going to match because we have a bigger ratio here. And indeed, it is now 8.74 after the addition of hydroxide. Okay, so we compare that to the 8.63 we had in the original buffer, added some hydroxide, and it went up. It went up about 0.11 pH unit, as opposed to if you were to put this much hydroxide into pure water with no buffer, the pH would be much higher. So this buffer has done its job. Yes, the pH changed slightly, but not nearly what it would have done without the presence of this weak acid and its conjugate base. Good job, buffer. Good job, bro. All right. I hope this exercise was helpful for you as you are working through problems with buffers. Thank you for being here as always. Thank you for supporting this channel and for sharing this channel with other people you think that it would help. And all of the comments and likes and subscribes, all that has just been wonderful. I have appreciated it so much. I love teaching chemistry. I think maybe you could tell that, possibly. And I get so much enjoyment from it. And part of what I really enjoy is hearing how much it's helping you and how much you are enjoying it. And any questions you have, any requests that you have, please share them with me. Let me know. Let me know what would help you. I am here for you. And I will see you next time.